Good. Today it's the crazy thing theorem in application again. The A, B, C, D of a unitary group in 2 dimensions, and its applications to mainly polarization, but we'll mention the other ones as we go along. The thing today that is probably the most intensive will be the development of the group product algebra, so that you can actually very conveniently multiply 2 elements of the unitary group and get a third. That sounds like it should be easy to do, and for finite groups we have really easy ways to do that, but this is a major calculation, and once you figure out how to do it right, it becomes a lot simpler. We're also going to talk about a geometrical procedure for doing that, and it's really due to Hamilton, but he didn't make it very public, so very few people know about this little trick that involves reflections. And that's the other thing that we need to talk about today, is the role of reflections in group theory. And it's primary and fundamental. And that's because even in a one-dimensional space, you can still do a reflection. Rotation's out, you don't have enough dimensions. But in every other space, there's going to be reflections for every dimension, and then combinations of them. So all of our finite groups are going to be built at first out of that, but I want to show you how the Pauli spin matrices, Hamilton's quaternions, without the I, the things that square up to 1 are mirror reflections, quite literally. So without ado, we're going to go on here, but I am going to pause in the middle here and to do a little bit of physics. This really belongs to lecture 9, which is its duty list is up here on the right-hand screen, and we're going to be looking at the ABCs of the U2 dynamics. We've already seen a little bit of the B-type motion, bilaterally symmetric pendulum that had a bilateral symmetry, but I want to look briefly at A, and then the shall we say, the big kahuna, if kahuna were spelled with a C instead of a K, is the circular Coriolis ... dynamics that is associated with elliptical polarization, circular polarization, and the various things that have chirality and current. So let's go ahead here and just take a look at a few of the things that will maybe help in reviewing what we did in lecture 7 previously. The main thing that we made a point of at the very end of that lecture was that there are 2 worlds. There's the spinor world of 2-dimensional complex or spinor space, and then there's a 3-dimensional world that we feel comfortable in because it's a real 3-dimensional isometry, you might say, in the vacuum. The 3D real vector space, R3 is the group that goes with that, and we'll be playing with it simultaneously that we play with the U2 group that goes with the other one. And remember that what we did was put down 2 kinds of notation for the same thing, this combination of the A, B, and C spinors and the unit matrix, which makes up the 4-dimensional Hamiltonian, has 2 names, one associated with, or 2 notations, one associated with a spinor space and another one associated with a 3-dimensional space. And factors of 2 are involved in the notation. Little omegas are angular velocities of the rotation that this Hamiltonian will eventually engender. And the little omega that is here a minus d over 2, and down here it's a minus d. So I've taken the 1/2 away from the parameter and put it on the operator, and now this is what we would, in angular momentum theory, quantum angular momentum theory, call the most fundamental elementary spin angular momentum component. A, B, and C. We do this with all of the parameters that are really active in the rotations. We don't make a big deal about this change here, the overall phase. We worry about that afterwards, essentially keeping those equal to each other in this go-around. So here are the ABCs, and there they are labeled either for what we're used to in ordinary quantum mechanics of angular momentum, where this is a spin operator, and this is an ordinary kind of omega that we're used to in our three-dimensional space. But behind the scenes, and that's the real point of this, I think, is that the more fundamental descriptions, plural, of nature are gotten by looking at the spinor space. It envelops, that is, the word is, it's the covering group, U2 is, that includes the rotations. And as we go through this stuff, both now and in the future, the idea of that will become clearer. But the other thing that I wanted to show also was the actual operators that this generates. And by generate, I mean putting this in an exponential with a minus I and a time factor. That generates a rotation of some kind. And in fact, with the time explicit, it's a rotation that moves in time. So this is the dynamics gotten by a Lie group element that has been generated by a constant matrix, at least constant for this particular lecture. Later we start wiggling these parameters, but that's something for another day. And there's a object called the crank vector, which is simply proportional to a vector made out of the coefficients omega A, omega B, and omega C. And we have them in that order here, A, B, and C, when we listed them here, and then we'll be listing in our vectors, our three-dimensional vectors, that way as well. And of course that's not quite the order you're used to, because A is Z in the standard language, B is X in the standard language, and Y is what the C here is in the standard. Okay, so we're going Z, X, Y. It's a cyclic permutation of those three. Okay, so the cleverness of this all comes with the stuff that's in the exponent here, which of course is this, right here. This is where it's written out. And you can see that we have these dot products between a set of numbers, either the little omegas that are being used for the spinor space, where I have A minus D over 2 and the plane B and C, or, and this is the thing that we do to make the, take us out of the half-S spin space into the space we live in. Here is an omega here that represents a higher frequency, and so we have the omega dot S equal to little omega dot little s, Greek s, sigma. And again, the time phase is being, overall phase is being factored out from the thing that does the rotation. So today we're going to be studying the effect of this operator in some animations, but also in some detailed mathematics, which involves the group products of things like this with each other. And of course the crazy thing theorem is behind all of all of this generation by exponent. Okay, now just to refresh the notation a little bit better, the operators that we're going to be talking about are best described, in my opinion, for someone that's interested in physics, by a machine that has a crank on it, and that object is sitting on the desk, and we're going to play with that a little bit today. But this is the axis of that crank. This is the thing that's the driver. And when that thing acts, when that thing turns by some angle phi, that means a rotation around this axis by whatever that angle is. And that's the, you know, the pristine, pure SU2 picture. And this, I say not so crazy because I don't have an eye on it right now, but of course we're going to be exponentiating the quaternion version, which does have a minus I attached to all of those. So these are just to show the two notations that I think are most confusing at first for this. This one is the original vector right here, whose length depends on the value of that angle, you see. Whereas the unit spinner that this thing is representing, remember, a sigma of some component in some direction, the direction being represented by a unit version of the vector that is this long, and this is a unit sphere here, so it would be coming out of the sphere right about there in this drawing. So that would be the unit sigma dot, and we're having a unit vector there, literally, that vector with its components A, B, C, D, and all that, has been divided by the square root of some of the squares of those A's, B's, and C's. So it lacks any other coefficient. This thing squared is 1, whereas this thing squared would be 1 times phi squared, whatever that length was squared. So we have to be aware of these hats, these little unit indicating that the vector that sits here is a unit vector. And most of our formulas will be based on manipulations of these angle vectors that are representing a rotation by some amount, that's the magnitude, but also in some direction in this three-dimensional space. And the machine we have here is adjustable to set a range of directions in the space of 4 pi, if you like, the whole darn thing, but this machine only takes care of the upper space. We have ways to fix that. Okay, so the crazy thing theorem, you remember, is something that squares to -1, and that's really the thing that we're working with here. Let's see if I can say anything further about that. Here is a sigma sub phi. That means a unit vector component A, a unit vector component B of the phi, and there's a unit caret there on each of those 3 things. Okay, we're multiplying a whole thing by a sine of phi, also a minus I, and then we're dotting here. That's what this component is. This is sigma A times this number here. This is sigma B times that number, and so forth. Okay, so that's the thing that comes out from the crazy thing theorem, is we want these crazy things that are sitting right here to have a unit in the sense of its square being -1, or I times it being +1 squared. Okay, so that's the actual picture of this thing again, according to the crazy thing theorem. And here is the complete and final unitary 2 matrix written in terms of these unit values here for a particular angle. In other words, they're interested in the unit of this thing, not the magnitude. The magnitude's being taken care of by the angle that goes here and here in the sines and cosines. And we'll see that at work fairly shortly. Now I'm going to go ahead and take a few cases just to, really cement this, this whole idea. We've already looked at case A, that's the asymmetric diagonal case, in which I have only made here a operator that's associated with a rotation around the A axis. And I've got the geometry here lined up the way Pauli would like it. That is the z-axis right there. There is the x-axis right there, which we call B. And there is that y that we're going to be talking about and having some fun with that we call C. So this one is just a diagonal with a phase. The minus I times the angle and plus I times the angle, that's just associated with exponentiating 1 and minus 1 there with the I, and a minus I is showing up here, and then the plus I right there. And this is corresponding to the unit vector of A type, asymmetric diagonal. And it's just got a 1 and a 0 and a 0 in that operator space. And right now, this 1 here is represented by a vector that's right there. Okay? And then if you do a rotation around the B axis, this axis right here, this is what you get. We haven't looked at this one explicitly, although it's buried in this one, this general formula here. But this is a rather strange looking rotation matrix with eyes, both of the same sign, off diagonal. And then the one that is more familiar to us, even though this is the weirdest case, case C for the chiral case, this is the one that makes an actual rotation matrix. This is the one that would be causing oscillations to form elliptical and circular motion. So they're each the different unit vectors in this space. But then, of course, you can have any linear combination of these, and that's what's being allowed by this and the whole idea of the crazy thing theorem. So perhaps what I should do, before we go on to any of the arithmetic of operators, is show a little bit of the physics again, but it's some more information that you need to appreciate. So what I'm going to do is I'm going to jump into right away lecture 9, and we're going to go to I think it's page 45, or in the neighborhood of page 50 is this one. I'm going to look at all three of these and let you see them in action. So let's go ahead and put the camera on this side over here, and I will attempt to, and that's the other thing, is the machine is actually in the way of some of this, isn't it? Which is a little bit unfortunate. That's probably making it a little easier there to see.
Just clipping your screen.
We're going to have the dynamics going on in the upper part of the screen, so it shouldn't be too traumatic, I think.
Good deal.
So let me go ahead and jump up and set this thing on page 45, just down here's a ways, where the this all begins, and this would be it right here. So this would be an asymmetric diagonal type motion governed by a Hamiltonian that is just a combination of the unit operator, that's the thing that does the overall phase, and sigma A, with some, and now we're using the grown-up notation for R3, uppercase omega sub A, and that's what's going to be driving the motion here. And got it?
Mm-hmm.
Okay. What we're going to see here is the effect of this crank that only has an A component. Now, the thing I should mention is that the spin vector, which you'll see turning around in there, will be usually flying around. But if the spin vector happens to line up with the crank vector, doesn't move. That's the real lesson today. Is the eigen states of this operator, that is the own states of that operator, are represented by spin vectors that point either along or opposite to the crank axis. So what we're going to see in the animation is stuff like this, and I want to show that by switching over right now to the program Color U2, which has that. I'll just go ahead and start it up. Now, right now, what you can see from the animation is that there are two pendulums swinging back and forth. We're looking down on our pendulum device that we have, but there's no coupling. All there is a slight difference in frequency for those two pendulums. One of them is a little bit longer than the other. Okay? So the one that's a little bit longer, here you have square root of G over L as an angular frequency. The bigger the length, the slower the pendulum. So this is a long pendulum, and that's the shorter one there. And this is going ahead and plotting the coordinate values x1 and x2 against each other. So you see the same sort of thing that we were seeing before, more or less, of what look like ellipses evolving from one shape to another. And in this case, the eigenstate for this thing, which I'll show very quickly here by starting the thing right here on the x-axis, are just one pendulum going back and forth. So all of the oscillation is isolated, localized in x1, or another one would be have x2 move and x1 stay still. That type of motion is stationary. That is, it is not changing as far as anyone that can't see the actual vibration. It's just making a line going back and forth on it. However, when you start it, say with, these are the normal coordinates, they're just x and y. Let's start with a lot of x and a little bit of y. Now, since they're different frequency, you can see this is not stationary. It started out as a line with the slope of their coordinates, but it's now turned into a tipped ellipse. And this is all stuff that relates directly to Stokes polarization. And what we have on the upper portion there is an actual spin vector slowly precessing around the A-axis. The A-axis is where the crank is, and the spin vector right here is very slowly precessing because I haven't given it much of an angle with the crank. However, what we started with, which is up here, where they had equal coordinates, x and y, that starts us off on the B-axis. Remember, that's the bilaterally symmetrical eigenaxis. So now we have the spin vector spinning as fast as it possibly could. Now I have to go back and restart this thing a couple of times to make a clean picture here. But I'll start it where we left off, and that's with the spin vector right on the B-axis perpendicular to the crank. That's the biggest trip it can take. It is as far from the crank eigenaxis, you might call it, as you can be. So it's going on the fastest, I should say the most longest trip that it can take. And then all of its trips have to be taken on a sphere. The length of the spin vector is constant. So this is the biggest trip. It's the equator of the motion that is there. And now it's very close to the C-axis, and you can see we're getting a circular motion here as we pass the C-axis, right? And it's right circular. It's a right-handed circular. Now, it was only perfect circular for an instant, but then it becomes an ellipse that's tipped more and more toward contracting onto the what we would call the minus B axis, the minus bilaterally symmetric axis. And there, of course, are two of those axes. We started on this one, and now we're closing in on this one, and the spin vector is closing in on the B axis. You see, and all this is being done with just two uncoupled pendulums. This is the asymmetric diagonal case. All right. Now, before I go on, if there are any questions that you can think of to ask about this, I remember you had a question about what is the relationship of the spin vector, right, to the state of the spinner, and I told you the answer was the expectation values of the A, B, and C operator. Those determine the coordinates of that spin vector. So this is an evolving expectation value that's going on here, and that's because the Hamiltonian is driving this thing. This thing is not in an eigenstate. It's as far from an eigenstate of the sigma A operator as you can get.
Sorry, if these two objects are not related to each other, why we see some difference in their phase?
If these two, what, are not related?
These two objects, you said that these two
Oh,
objects
these two are not
related.
coupled. There's no spring between them.
Yeah. Why we see some changes in their phase?
Oh, because in that particular Hamiltonian that we have, I have some parameter here, a plus d over 2, and then I have some parameter a minus d over 2, determining the actual speed of this thing. This is just the pure rotation that you'd get. But the full Hamiltonian is going to have the ability to put a value of oscillation here on the x, which we call A, and this one would be D. Those are the two coefficients that are active right now. B and C are 0. B and C are off diagonal. B and C are couplings, and we've terminated those. We're only dealing with a diagonal matrix.
We have A here.
We have A and we have D.
And B.
Right? So A
Can
plus
you make
D.
one example?
A plus D.
For example, one example of real.
In the case of the pendulum,
Yeah.
It's
Or
a cable
pendulum
clamp.
or a spring.
yes. The basic idea would be to take this thing away,
Yeah.
okay? So that's not allowing them to see each other, right? But what I can do, you see, is make one of them faster than the other, you see, by raising it up, okay? Making it be faster than this one. That's equivalent to changing the coefficients A and D. Basically, this could be A and this could be D, okay? And then what I'm doing is I'm saying, okay, I'm just going to start some motion here, right? And that's what you're seeing simulated, with a slight variation in these speeds of them. Okay? Now, we're going to come back to B, so I better not lose my coupling spring. I'll put it right there. The same animation, and we have to do this twice in order to get it, but if you were to make them very different, you see, then they're very quickly out of phase, you see. This guy's a lot faster than the other one, okay? And you can make it even more so. This is the fastest one I have set right now. I imagine this guy really fast, okay? So now you're seeing basically almost Lissajous patterns, right? Because this one is so much faster, okay? And look how fast we're going around the circle up there in the ABC space. The spin vector is really turning. So it's responding to the differences there. Now, we could switch back to this. Let's see. No, actually, what I have to switch back to would be the lecture number 9, and I think I'm going to go ahead and try to do that. Let's see if I can pull that off without too much trouble here. I will go ahead and escape from this and go over to the 9th lecture here, page 45. And I think I can do that very quickly. And I'll start right out in the middle of that particular case, the A case, which is this one right here. Okay, so what we've got is a crank on the A axis. Now the A is up here, the A is to the side over there. The A right there is cranking every point, any point I have on a sphere is going to be going around at a frequency that's dependent on how different is slow and fast. That's really all there is to this. And the difference between those two eigenstates, omega A over 2 and minus omega A over 2, okay, the difference between those is omega A. That's the beat frequency. Total beat frequency is the difference between those two. And that's the 1/2 coming in again. Omega A is A minus D, you say. And we've set B and C equal to 0, so those are out. Only got a crank in the A direction. Okay, does that make sense? You wouldn't think you'd need all of this powerful mathematics to take care of two things that are just swinging by themselves. But the point is that everything we're doing here we just do over again for all the other cases, except the physics is very different. Okay? So on this thing, the next stop here is a bilaterally balanced type motion. And that's what we're going to study next. And this one involves just this matrix right here and the yin. You see, we can still have something in it provided, in this case, we make A and D equal. It has to be bilaterally symmetric. So this has to be a unit matrix, and then we add the B. Okay? And the coefficient of that thing right there, okay, and that's sigma B right there, and there is sigma B. That's going to be omega B over 2. We've got to put that 2 in if we're going to look over in a three-dimensional space at what's going on here. Okay? So what we're now going to see, if I make that coefficient negative, if I make that negative, that's the best way to show something that's physically true for both the classical and quantum mechanical applications, like in ammonia or our pendulums. It's going to have a crank vector sticking out of the back door of B. It's going to be negative B. So there's the crank vector omega, vector omega, that's going to be at work when I start the simulation. So let's go ahead and I'm going to set this thing up for that case. Our second case is B. And there it is going. And I'm starting off on the x-axis this time. Remember, that was an eigenstate for A, but it sure as heck isn't an eigenstate for a B operator. And the crank, in this case, is indicated by, and it's being covered up by the spin vector as it passes. This takes a little bit of three-dimensional visualization that we're going to be improving in our new program. But there is the crank sitting there, okay, and it's a right-hand motion around the crank. So thumb into the board causes me to have what you're seeing. And we're just passing the C-axis now, so there's a circle being formed, and both phasors are equal, and we've got this pi over 2 phase lag between them. And by that I mean the leader here is leading always by pi over 2. You see, always 90 degrees behind the follower, which makes, when they're equal, a circle. So that's something to remember. So we're just about ready to come back on the minus A axis in spin space, but that means we're coming back on the Y-axis. Right there is a stopping point, okay? I'll try to stop if I missed it, but oops, I missed it again there. I'll click there and that should stop it. So here we are in a moment just past where we were oscillating on the y-axis and getting ready to now switch roles. This right here will now be the leader, and you can see already he's 90 degrees ahead of the tiny follower here who is growing because of it. And that's a basic phase relation every engineer knows. If an oscillator is ahead of another one, any linear connection between them is feeding energy that way. You see, the leader is giving, always giving, you see, and the follower is always taking. Takers and makers, right? Political world, okay? So, that is the basic idea of that, and it's worthwhile seeing it go a little faster. Now the crank's really going fast. We've got a big strong coupler between there, and we've almost gotten to the point where we're on the y-axis again. And of course, we don't stay on any point very long with this one. This is a very strong coupling, so it's driving this thing around the space there very quickly. Okay? Now remember where we stopped, and let's see where we are when we finish on the other side of the A world, right? You see, we started here, right? Okay, that's A represents the x-axis. Okay, but minus A represents the minus x-axis. You see, we're not home yet. We're over here. That's the minus sign that you get from going 2 pi in the three-dimensional world, you see? In the two-dimensional world, you're not home yet. You're on the x-axis, but you're on the minus side of it. And that minus phase gets you out of time by a complete half cycle. That must mean 180 degrees out of phase. So this is where you really have to take seriously that minus sign, right? Because you're on the other side of the world. You see, this thing looks like it's home. Now it's going to continue now. You know, it's going to continue around, okay, and eventually come back here again. And by that time, this will be home. Okay. Now, unfortunately, I can't just get this thing going again. We used to be able to do that. For some reason, that doesn't happen anymore. So we'll just start this over again and go all the way through. So there we started. Now we're at the quarter wave plate, if this was optical polarization, okay? And now we're getting toward the half wave plate where we are right there on Y polarization. And now we're coming back with left circular, you see. And now we're about to get to a home, you see, and we're on this side, okay? Now we're going to go around again, okay? We're just now getting ourselves with right circular. We just passed the positive c-axis. And we're just about there on the y, okay? It was negative y, I think, but it doesn't matter. Anyway, now look where we're going to be. We should be back here when I return to A. Bingo. Okay? So it took 4 pi to get around this thing in order to get home in the spinor space. And this is the spinor space. This is spin up, spin down, if you want to, you know, play that game, as you would with electrons, you say. Then that's an actual spin vector for an electron. But you can see how polarization is a lot easier to see, right? It's more classical, you see. And classical is providing you with an easy visualization, okay? So, the same deal is happening here. Sort of things that we're showing are all going on here. Now, again, the total beat frequency, omega b, that's what it is. That's what's actually, we're actually looking at. An engineer would call that the beat frequency. You say omega b is the beat frequency. But when you're making these beats like this, I say that that's half a beat frequency. I still have to finish it down here. So I would say I need a half. the engineer's beat frequency should divide it by 2. It's not as fast as he thinks. The period is twice as long. You got to go through 2 oscillations of the envelope to do a beat. Subtle point, but those 1/2 are the devil in this in the details of this U2 dynamics. Okay, I will stop at this point and get ready for the C, if you're ready for it. Okay, the C
Just
is...
before that, can
Yeah.
we have one example of B,
You mean the real?
the real?
Yes. That's going to require us putting the coupling back. Okay? Now, it's also going to require us making sure that this thing is more or less tuned without coupling. Okay? And it looks pretty good. I think there's more friction on this side, but aside from that, I think it's pretty good.
Mm-hmm.
Okay?
One side has some.
So, now we're going to put the B in. Okay? And I'll start out with, medium strength, right about here. And strength is determined by leverage in this particular system. So the higher up I go with a spring, and the weaker the spring looks because it's out of focus on the screen there, the longer it's going to take for me to go through a beat. Okay? So I'm going to start the thing off at +2 or 2.5. Where I'm looking at is about 2. And all my energy went up, and then that one's standing still, and so forth. Okay? So that's a pretty quick set of beats, right? And then I can make it so that it takes a lot longer. Okay? So let's see how this works. Even with the friction, it's pretty smooth. It's completely lost its energy there, right? And then return trip. Okay? So even with the friction going, it isn't hurting the friction. Friction is only just decreasing the amplitude, and everything that we're talking about here is happening, right? So that's a good example. Now, unfortunately, I have no way to do the C on this machine. The possibilities we're thinking about. But A and D and B I can do, okay? And we'll talk about what happens when you mix A and B. But let's just go for C, okay? C is coming up right here. And there's the C axis on this graph. And then the C axis that we've been working with is where I think it belongs, and that's up. You see the C axis up in the air there, and the Z and A are pointing at you. A little bit different from this one, where the A and the Z is up here. This would be more a normal drawing on the one I use in the textbook. Okay? So what we're going to see is if I start off with linear polarization, boy, that is not an eigenvector. That is as far from being an eigenvector as you can be. And we'll go ahead and start this one that way, I think. We will. Let's just see what happens here. Okay, so this is a slow motion C symmetry animation. Are you ready? I don't know if you can see what's happened there, but my X polarization is rotating and staying pretty much linear polarization, which is what you'd expect. Our little spin vector is now moved away from the A axis, and it's headed toward the B axis. And when this gets to be 45 degrees, which is half the 90 degrees between A and B, that's what you'll be seeing here is B-type motion. There's when the spin vector is on the B axis coming up right now. Okay, so there's a 45-degree oscillation briefly, and then it's, of course, moving on. All right? Now, what mechanical device exists in museums that does exactly this? And almost every big museum has a Foucault pendulum. Big pendulum stung way high, and it precesses. Right, as you wait 15 or 20 minutes, you can see it's precessed because of the Earth's Coriolis force. And it depends on your latitude, you see. When you're on the equator, it doesn't work. But when you're up at latitudes like this, or further north, it works very well. And finally it gets up to where it's simply tracking the fact that the Earth's turning under it, and, you know, it's going around it like a regular clock. It's a 24-hour clock. There we go. We've just gone to the opposite side. Okay? That's the opposite side of the A-axis, which is the Y motion. All right? So the idea is that you could start this thing up with any sort of initial conditions. If I start up, say, right about here, and you give it a little kick this way, it's going to make an ellipse that precesses. So this would happen if you went into the museum and kicked the pendulum just when it came. Of course, you'd get thrown out for doing that. But it would do this. It would then make an ellipse that precessed just like the planes did. And it would represent by a spin vector, you see, that was either, in the case that I gave it an ellipse this way, was in the lower plane, or, and I'm about to run out of time here, I should start this thing again right now. And in fact, let's start it with some speed. Let's make it really go, okay? This is a half speed. Now you're starting to make these pirouette loops, you see. It's almost to the Y there, right there, okay? And then it continues. And what I'm showing you are its two eigenstates that combine to give that trajectory. You've got equal amounts of both of them running right now. So you can see one of them's going around faster than the other, and that's what the Coriolis beating is consisting of. I'm going to go ahead and jump ahead on this so you can see that that is the mathematics the same as the other ones, except the physics is very different, you see. This thing has current, chirality, and curliness. It's a C-type motion. Okay, really hard to read the phasors. We're not used to reading circular phasors, but there are ways to do that too. So this picture over here of the omega c over 2, same deal. Okay, the actual beat frequency between those two left and right motions. And I'm going to try to reproduce, if you don't mind me swinging you back to the other screen, I'm going to try to reproduce a right-handed circular polarization state. Okay? And the way I can do that on this one is very easy. I just drag my initial velocity out until I fit pretty close to a circle. So now I've got my spin vector on the c-axis, almost, not quite, but almost on the c-axis, and you can see I'm pretty much just making a circle with a little bit of the, I've got mostly right-handed, but I've got a little bit of left-handed in there, and you can see it's making the thing make a fat trace. So I think now you begin to get the feeling for what it looks like to have a spin vector and a crank in the picture. You see, the crank just sits there, and the spin vector will go around it at some frequency that depends on the parameters, namely, in this case, just the omegas. And if that spin vector can be put right on that crank vector, and I'm about to run out of time again here, I'll try it on the left-hand side. This is, no, that's the right-hand side. Let me try, there's the left-handed side. I'm going to try to get right in the center of that blur there. It's pretty good. Okay, that would make a sharp circle, which has a different frequency, you see, than this one. You see, these two eigenstates are differing by exactly the beat frequency, which is 2/2. This is a spinor frequency. That's what we really, engineers will read off, you see. They're looking at the three-dimensional picture here. Okay? Now, this is, all this stuff works no matter what the parameters are. They can be really fast, like this one. These images were left behind. It's just a fault of the program, but it does show you where we started. And what I want to show you once again is when you go all the way around in this space, you're not home. See, we start off with an oscillation that's this way, this way, this way, this way, this way. You see, that's what we call a zero. And we come back out of phase again, right? If we started pointing that way, we're coming back pointing this way. And then we go around again, and we'll come back pointing the way we started before 4 pi. This is a three-dimensional space, right? So things go twice as fast in this space as they do in the spinor space that we're looking at with our pictures of the x and the y. And you can see why I don't use x, y, and z for A, B, and C apart from the mnemonic. This one deserves to be called x and y because that's the polarization space, x and y. That goes back to 1843. Okay, so, all right. Now, the thing that we still have to learn is how to handle all the cases between these three. And I'll just show you very briefly one case. This one. This is where the crank vector is just a little bit off the a-axis. And what do the eigenvectors for such a thing look like, you see? And the answer depends on how you start this thing, but basically what you're going to have to do is make some kind of ellipse. And I'll go ahead and let the computer do this for me. Here's actually, I'm sorry about that. I started with a simple one. This is a case where the eigenstate has a little bit of a slope. That's one eigenstate. And you see what's the difference here is I got different mass. Okay? One eigenstate is there. Another one is right about the same position perpendicular to that. Right about there. Well, I didn't quite make it. It's a little bit off. I think I can come a little bit closer and do better. Or I can ask the computer to find it and make that perpendicular. But that's where it's going to be. You see the potentials in there? The whole thing is tipped over a little bit. So that's the combination of A and B. It's still plane polarization eigenstates, no curliness, but it's not right on X and Y or halfway between. B is halfway between here and here. You see, are there eigenaxes in polarization space? If you have a B-type birefringent crystal, right? Another B, okay, for the B-type, all right? If you have that situation, there. So, go ahead and just quickly show it. There's the eigenstate right there, okay? So this is an eigenstate where the two masses oscillate in phase. With this one, the big amplitude, and that one just a little bit of amplitude. This could be gotten by perturbation theory because there's not much difference from the original situation. Okay? And then the other eigenstate, the one that we started with, is right here. In this case, the big fat mass stays at home, and the little one oscillates back and forth out of phase. It's plus minus. This one was plus plus. Okay, so that's something to keep in your mind. We'll come back to this, but you see it's being shown very clearly by where the spin vector is in this picture. Now, as I say, where we really need the computational stuff that we're going to be talking about in just a few minutes here is for cases like this. Where the two eigenstates are both ellipses. And the spin vector is out in the middle of the space in between A, B, C, and D. It's not in the AB plane like that other one was. Okay? So here we're looking at first an eigenstate that looks like, if I can get it here, this one. That's an eigenstate for this particular thing, where I have A is 4.83, B is 0.24, C is 0.42, and that's, let's see, what is it? The D is there is 4.28. Okay, so everything's, there's no, you would say there's no symmetry here, but still there is a unitary symmetry that's following this all the way into this jungle. Okay, that's one of them. And then here's the other one just peeking down there. It's an ellipse that's orthogonal to that ellipse with its aspect ratio more or less the same. So those are the two eigenstates. One spin up, the other spin down, but in a crazy direction, right? Somewhere in between A, B, C. That's what we need to quantify very precisely, because if for no other reason, one of the most powerful spectroscopies is polarization spectroscopy. I mean, we're using it on the Big Bang, okay? That's one place, but we really don't know what the hell's going on there. But in crystals and in molecules, we learn a lot by looking at the polarization. So we're going to swing back to this screen and go back to Unit 8 and get busy with the arithmetic to the meat of the thing that we need today. We just looked at A, B, and C, D, and then some. But I don't have to remind you again that we have to do this half angle business. And that means replacing all of our formulas with these uppercase thetas. So this is that same matrix that I showed you before, but with the substitution of the uppercase in there. And of course you see it's always divided by 2, because it's twice as fast as the spinor space really wants to go. So this is the general matrix that we'll be using off and on to calculate with. And I call it the Darboux representation after a geometer that really had a good concept of what a crank was supposed to do. I noticed that I enlarged the screen here a little bit, so I'm getting some flow over the bottom of the platform here. In any case, what we're going to do is we're going to play with the group using the parameters associated with this crank. And they're just polar coordinates. We're going to start somewhere that we call X and have an azimuthal angle for this crank supporting frame to rotate around the Z axis. And at any point that I stop with my azimuth, which will be a italic phi I will have an italic theta that I can set on this arm right here. So I don't really need to make the crank go down into the basement here, because it would be the same, getting a basement rotation would be the same as if I just turn the crank, and that's the main thing. The big theta is the axis angle dial, big theta, and that's what this dial is right here. I would just simply turn it the other way to take care of all the rotations that live in the basement. Anyway, that's the operator's parameters. Now the spin vector's parameters, that is the little body z-axis that lives in this sphere, its parameters are S-mu alpha, that's the z rotation of this bar that's supporting the beta dial, which is supporting the gamma dial, which is supporting the body. That's quite a nice connection there that you see in front of you with the actual device. So there's the polar angle beta there. There's the Euler cousin to this guy, this polar angle right here. You see, very different context. And then the azimuth, this azimuth, the laboratory azimuth, is the operator cousin, the spin vector cousin to this azimuth. But as you can see, very different context. These are coordinates. This one right here is the azimuth people in the body would use to measure the zenith of the laboratory relative to it. In other words, what would be cut in this frame. So we need to talk about these polar coordinates, x, y, and z. Now we're going back to the older notation, but remember we're going to be coming back again to a, b's, c's at any point. So this is just something I think is really important, and what we're going to learn in this course is you have to take both of these seriously. Both of these represent a different set of group operators. Not different in their multiplicative structure, but different in their physics. One of them is the one that everyone's used to, which is in a lab frame. Everyone's used to group operator acting in the laboratory to move some classical or quantum mechanical wave object. And what I'm telling you is, if you have that, then you also must have and pay attention to what it is happening to the bodies. You have to get rid of your chauvinism and realize that they are waves too. And they're watching you with another group. I call it the Mach principle that reads on that. So, what we're going to do is we're going to talk about operator on operator multiplication transforms, whatever you want to call them. Just a brief review. We have a multiplication table for the spinors, Pauli's, sigma, x, y, and z, our a, b's, and c's. And we also have quaternions, I, j, and k. I call them x, y, and z here. That's not something Hamilton did, but all I've done is take the I off. So here are the two multiplication rules. Quaternions give you that. This is what the spinors do, and this is the epsilon tensor. This is the way you find it in a textbook, if they were to tell you what the algebra is. I want to point out commutation rules, which are the differences between this and this. That's the commutator, right? Okay? Same basic idea, except this cancels out and you're left with two of these. There's that annoying 2 again. Okay? You get rid of that 2 by defining an operator that is sigma over 2. Bingo, you get commutation relations you're used to. Okay, so just another connection to the usual way of doing things, okay, that you should be aware of. Okay, once again, it's 2.5. You always can use 2's. All right? Okay, now we're going to see that again with this business. What I want to do, and I want to make sure that we pull this off before we run out of battery or I collapse, the Jordan-Pauli identity will give us a group product formula. That's what we're after here. You can also do this and this. I'm going to leave those for later or an exercise that's coming up. Now, here's the idea. I want to take an operator that's characterized by a crank vector, and this is not a unit crank vector. This thing has a direction and a length, so the little arrow on top of that is, I guess, necessary to remind us of that. I had to put it there because I couldn't find a fat enough theta to differentiate it from just a plain unbold theta. So you'll see the arrows on top of those, as well as on the spinor operators, which I've made a habit of doing that just to remind us that when a sigma doesn't have a component, I mean a vector of those sigma matrices. But these are the numbers we're used to, that we've been working with so far. Now, the idea is, what is the product of this crazy thing with this crazy thing? And it is not just an adding of exponents. These things do not commute, whereas complex numbers do commute. So I can do that with complex numbers. I can't do it here, except in a very special case that I'll show at the end. So here's a crazy thing theorem giving us each of these exponents. Okay, one for a vector theta A that's pointing out somewhere. Now here's the unit vector theta A, and that's where we need it. We need a sigma sub theta A, basically, right there. And that's our crazy thing that's sitting in the thing up there. Okay, and then this is the parameter that's up there, which is the magnitude. You see there's no arrow on this thing, and it's thinner, but not much thinner than the operator that it came from. But that's a number. Okay, how much did you turn around the A-axis? And this is the A-axis, unit A-axis, being summed over all of the Pauli spinors in general, because we're out in the middle of ABC space. So we got two of these. One was marked with a B in colored purple, and one was marked with an A in colored sort of maybe blue. So it's these two operators, and we want the formula for this one. That's what we're after. Okay? And if you're going to do Lee's stuff, Lee's idea, Lee's evolution, you definitely have to be able to multiply all of the group operators with each other, satisfy the group rules numerically. You have to be able to tell a computer to do that, and this is a formula that's very nicely put on a computer when we get done with it. But here's what you're going to do. You're going to take this times this. And first is this times this, which is these two cosines. Good start. Okay, we've got all the other stuff involving sigmas. Okay? So what I'm going to have is this guy right here times that sigma. Okay? And then I'm going to have, that's actually this term right here, and then I'm going to have this sigma here times this guy. Okay? So there goes that guy right there, there's this guy right here, and then down here it's this guy right here, and then I've got this guy coming up, giving my sigma. Okay? Both of them have a minus I in front of them, so there's a plus sign here, and then dotted with sigma. Okay? So we're just expanding the crazy thing into four crazy things. Then finally, here's the hard one, this guy with this guy. Two signs and two of these sigma sub A's. Okay, the unit guy. Okay? So far so good. Okay, now we get out from lecture 7, our little, called the Jordan-Pauli identity, really Hamilton's identity. But it's, you know, doctored up with Gibbs's notation. Okay, we've got the sigma dot A and sigma dot B vectors here. Okay, so the A and B are these things. So these things are unit. These are any old vector. Okay, so this is a general, more general than what we really need. It doesn't matter. We just use the notation as it is. So we've got to reduce this thing to that. Okay? And then sum the whole thing up. So we're going to end up with a whole bunch of things that consist of a combination of a unit thing and a sigma dot some vector thing. That's what we're going to end up with. Well, here they are. Here's the unit thing, okay? And we got that because there was a term in the reduction here, A dot B, okay? So we end up with an A dot B right here, right? And of course multiplying the thing that gave it, which is sine, with a minus sign, okay? That guy right there gave, for his first term, namely that term, this thing, okay? Then, here's the real meat. This is a minus I now for everything, a whole bunch of sines and cosines times unit vectors, okay? These are all unit vectors except that guy. Depends on what these two unit vectors are. That might be 0 if they were perpendicular to each other. So that can have any length, even though the components have unit length. Okay? So here are three terms making a vector to dot sigma, and we're going to match that with the crazy thing form for our product. This is the answer right here. The product comes out to be a cosine of some angle over 2. This is just a crazy thing being mimicked again, and then a vector times the sine of the crazy thing. You see, that vector being the vector that's multiplying the sigmas. There's the sigma, okay? So here's how it's really working. Is the first step is to take the coefficient of this 1, okay, this thing right here, and set it equal to all of these sines and cosines, and I have to know, of course, the dot product of the unit vectors that make up this product. Okay? So that's going to give me this angle, which will give me this angle, which will give me that coefficient, and then I simply have to derive how big is that vector, you see. That's the vector theta AB unit that specifies the direction of the axes in terms of the direction of A and the direction of B, and the angles that they are actually going to be rotating, which are those lower scalar theta A and theta B magnitudes. Okay, so that's our answer. That's our product right there. Let's summarize. There's the whole thing that we just said there. There's what you do. You got to find theta AB is the arc cosine. Now here's where you get in trouble, because arc cosine is not quadrant perfect. So you can get minuses and pluses as you go your arc cosine, depending on what program you use or calculator. But once you sorted that out, then you're in pretty good shape, because you then know what this is. So you use an A tan 2 to sort out the cosine and sine, and then this will work for you without fail. At least I have found that to be the case. Now, what about this? This should happen if the unit vectors for A and B are collinear. Then you're just doing ordinary, well, shall we say, one-dimensional rotation, which is commutative, right? Okay, so if they are in line, this is gone. Right? That's out of here. All I'm left with is this and that, okay? And these are in line, okay? So I just factor that out. I'm left with a sine cosine plus cosine sine. Same thing up here, okay? In line, those are unit, that's a unit right there. I'm left with cosine, cosine, sine, sine, with a minus sign, okay? Well, that's cosine of theta A minus theta B, right? This would be sine of this. So yeah, we're getting our we're getting the thing to give us that in this very special case. You will simply add them, but most of the time you don't get to do that. Okay, now this next business of transforming sigmas, and we're kind of close to the end, so I'm going to, as I say, leave this as an exercise, and it's a very useful one. It lets you do some things that are really cool. So is the general transformation or rotation. What I want to show, and this is something I'd like you to read, I'm going to go through it fairly fast, that all of this can be done with mirrors. You know how they always tell you it's done with mirrors, that's a magician, right? Now this is kind of magic. Here's sigma A, okay? 1 minus 1. What does that mean? It means I reflected in the y direction but left the x direction alone. So that just is a plane mirror in the x-plane. Okay? It takes the unit vectors x and y and flex them into those dashed ones, right? And then this thing does the same thing but around the 45-degree axis in our little spinner phase space over there. Okay? Note that if I just put a minus sign on this thing, it becomes a mirror in this direction, you see. Isn't that cool? Pretty efficient little reflectors, right? One matrix, except for a factor, does both jobs, right? And the same thing for this one. Okay? Now we'll talk a little bit about that guy, but that's going to be reflecting in this direction. Okay, minus 45-degree plane mirror as opposed to plus 45. All right? But what's really interesting is combinations. Suppose I take sigma A plus sigma B with some amount. That's what we were doing over there, by the way. All right? I take those two guys in combination, okay? Well, it turns out what that is going to give me is a matrix that reflects around a plane that is located at the angle phi over 2. Half angle, that half again. There's the half. That dastardly half. Okay? Now, if in fact that's true, and it is indeed what I'm getting here, okay, is a x component that is the cosine of phi, and then a y component is the sine of phi, so that implies that these are the matrix elements in the x column, cosine and sine, okay? And I go one step further, and I notice that this guy right here, which is made of sine and minus cosine, there's the minus cosine, there's the plus sine, goes with that. Minus cosine is there for the reflected vector. This reflection right here, you see, that implies in the y column I have sine and minus cosine phi. So this is the matrix that does that right here. That's what that sum is. You sum those two guys, that's the mirror plane you get. Put a minus sign on that and you get a mirror plane this way, perpendicular to this mirror plane. You see, mirrors are making things easier. Mirrors are easier than rotations. And here's proof, real proof of it. If I put these two mirrors together, suppose I do sigma first. Now we usually act on kets, so anything on the right-hand side is first. Whatever comes after that goes second. So here's the sigma A that's coming first, here's the sigma phi that we just made here coming second. And that gives you, presto, presto, a rotation by the whole angle phi. Twice this angle. Dastardly 2. There's a rotation, you see, that is twice the angle between these two mirrors. We've got a mirror here and a mirror there. This mirror coming first, this one coming second. Okay? That's kind of neat. Rotation angle of twice the angle between the mirrors. And it's minus twice if you do the other way around. If you let this guy go first and that one goes second, you get a rotation with a minus phi. But again, the phi, the magnitude of phi is half, I say twice, the angle between the mirrors. Okay, well this sets the stage for a three-dimensional way to do this. This is now bringing in C, and that's where it gets mysterious. Okay, this is an imaginary reflection. You put these two guys together with their determinant -1 and -1, and you get this guy with a determinant +1. That's how you tell it's a rotation. Both of these are rotation because their determinants are positive. Okay, This is a XY rotation by minus 90 degrees is what that one is. It would be that matrix right there with the phi equal to 90 degrees, pi over 2. But here's where it really gets cool. This is called Hamilton's turns, but it's really hard to find anything where he went into this in any detail. The idea is that if you want to do a rotation by this angle, you just get out two mirrors, make them intersect on the axis that you want to rotate around. So this could be in any direction. This is a three-dimensional thing, okay? And you look to see what the arc is between their normals. Okay? That's pretty telling. And the idea is it's a theta over 2 arc. Then, what do you do? No, and there's one important point. Important point about turn arcs. You may slide them anywhere on their great circle equator. You can put this thing anywhere you want. Of course, you'll be taking the mirrors with it, but they don't care where they sit. They're still going to make a rotation around this axis by that much, because they've got that much over 2 between them. Cool? So, if I want to take two different rotations, say I've got a Hamilton turn guy right here, it could be anywhere, and then I've got another rotation, this one's the first one, that one's the second one, here's what you do, okay? You say, okay, behind this one are two mirrors, an initial mirror and a final mirror, okay? And what I'm going to do is I'm going to line them up. I'm going to slide these around so they're head to tail. If I want this one to come first, I get the head on that one, and the tail of the second one is what comes next. Now what happens is, this is made of two mirrors, this is made of two mirrors, but these two mirrors cancel. Right there. They're out of here. I'm left with these two. And that means this is the arc perpendicular to the answer, the product. That's the product right there of those two operators. I think very cool. This is a way to visualize rotations in 3D. Not only that, but it works for all of the crazy stuff we're doing with polarization and electron spin, because it takes account of the minus sign, as we're going to see. You can represent a rotation by the Hamilton arc or its supplement. The supplement, you see, each of these get doubled. If each of these get doubled, the sum of them, you see, adds up to 2 pi. So in regular space, there wouldn't be any difference. For classical rotation, use either one. But for quantum rotation, you've got to call a minus on this one. And I mean a phase, the kind of phase that was causing us to get out of timing in that oscillator evolution. So, boy, this really sort of opens up a whole world of visualization for some really pretty hard to visualize things. It's doing the same thing that complicated algebraic formula is doing, that they will agree with each other. And that's something we'll look at as time goes on. Now, the rest of this is fairly, I should say, group intensive. We're going to really come back to this when we really need it. But I want to show you another factor of 2. I'll just give you the punchline here. The similarity transformation of this rotation right here, the red one, into the brown one is done by simply rotating by twice the angle you got to make these products that involve either one of them. That is a similarity transfer. This is an inverse, that's the operation. I can turn it around the other way. This is the inverse here, there's the other thing turned around. Either one of those are the green arcs here. And you see, the idea is that when you do a similarity transformation, you're literally picking all the hardware associated with the red operator and rotating it around that axis, and it will rotate, this diagram doesn't show it very well, but it will rotate into a vector that sits on the brown curve here. So this will come around the corner and be right there with exactly the same length. That's cool. This is really wonderful geometry. This is spherical trigonometry. If you go way back into the annals of the Portuguese navigators, as they explored the world, they had to do spherical trigonometry or get lost. Well, that's what we're dealing with here. Only we're dealing with spin a half, if you want. Just ignore the minus sign if it's a positive spin. So all of this is stuff that I'll have you look at later when we use it for finite groups. But it's really very cool to have this. I don't know of any books that makes use of this. Still, we published this in, gosh, when was it? 85. A referee liked it. One of the few papers a referee actually liked. There were two of them. It was called Double Group Theory on the Half Shell. You know, it was a recipe. Okay, I think we'll call it here. We've come full circle, and now here are the physical things. We have some things to say about that, but we'll do that next time.